from one domain to the other domain. And one example is this scenario that we're talking about of where we have data which are observations from the satellite, this is case before and after modalities, and the output is a map. So a label map, right? So this is what defines a classification process. A couple of last things, and then we're going to make it hands-on. Another scenario, the thing is active fire detection. So in the case of active fire detection, what you want to do is you want to have a satellite image and you want to identify what's the fire from, right? This is an interesting problem, and it's different from what is usually done in remote sensing, which is parent area mapping. So once there's a fire and the fire is put out, then you can measure how much land was burned. The question is, active fire detection is extremely useful because you can tell you now where the fire front is, and if you could somehow magically have this information instantaneously, you can control the fire brigade and so forth. Now, so this scenario was published here, so the user answer came to do active fire detection. So what is this? So we do active fire detection. So input, Landsat date, right? So my second element is for Landsat date. Output, I need labels. How do I find labels in this problem? So in this situation, before some humans, they annotated, annotation, either instruments, other instruments, and so forth. In this scenario, because we didn't have a lot of data, what they said to me was, we're going to take 3 standard techniques for detecting non-machine learning techniques for detecting fire from, which is first only the values of some bands, so like the ratio between band 7 and 5 should be more than 2.5, and the difference between those two bands, and blah, blah, blah. So there are thresholds. User-defined thresholds, like expert-defined thresholds, that the set of thresholds are fine. And when you put these thresholds, you can take an active fire map, send the image, and you can take the masks. But then the question is, okay, so wait, if I already have a way of taking observation and getting the mask, why do I care about machine learning? Which is a perfectly valid form. Right? So what the guys were trying to do is automate the process. That's like automate parts, it's already automated, right? So we already did that. So the guy said, okay, so maybe none of the 3 off-the-shelf threshold-based techniques are good enough. What happens if I extract all of them and then I use voting or intersection between the predictions and use this as a ground truth for the training, for training the neural network? And it works. Right? The neural network is a new UNet. It's a UNet because I'm taking an input, an image, and I'm taking an input as output, a mask. Right? So UNet is the thing that you're looking for. So okay, so this is the UNet, this is the data, and that's a one way of what I think. After the guy said the paper published, then it's fine, right? So there is this way of actually doing that. And then these are some results that they have, and they demonstrate that in fact we can have a very lightweight UNet that's able to detect that, and the performance, the holdout, the small holdouts set for validation, and they demonstrate that even if you train a neural network with somewhat, fuzzy quality labels, because they're automatically generated, like some user actually did that, so it's automatically generated. Even if you do that, you might have a situation where the CNN, even a small one, is able to actually, the unit is able to identify and correctly classify and segment these fire maps. Right, so this is interesting. This is sort of tries to address the question is what happens when I don't have the ground truth data? And the question is, can you find a way around it, right, somehow? Another topic that you sort of saw, but we're not going to go into details, but just to give you a hint, is the option of object detection. So you're given an image, and the question is identify the objects in the image of interest. So if this is the only slide, so this is just the keywords. So the first keyword, the first technique is called the faster RNN. So this type of those 2 types of networks, that's what makes a really big stride between the pre-deep learning and the post-deep learning, is the techniques where in the pre-deep learning, we would take an image and it's like, okay, scan this image now for airplanes. Now scan this image for ships. And so you sequentially scan the same thing for all the different objects you're looking for in the hope that you'll find them. And if every image is one out of 100 different objects, so you see 99% of the scanning is a waste of time. So this type of deep learning based approach is what follow this idea of YOLO, you only look once. So you have the observation, you have the image, and you extract things automatically so that they identify all and have the object at once without scanning it repeatedly. Right, so there was this idea that we had you take the image, you do the convolutional length, and then you have region proposals. So these are proposals where you might have objects, and then you do some pooling because there are some issues with detecting which bounding box is the correct one. So this bounding box is correct. Maybe one shifted a bit up and a bit down, all of them. So you aggregate all these bounding boxes, and this is what faster RNN does. And YOLO is the first edition. There is YOLO 2, YOLO 3, YOLO 4, YOLO 5, 6, 7, 8. I mean, there's like every sequence of YOLO, and every time they do it something to make it just a bit better. So if the question is, I'm going to have remote sensing observation and I'm going to do object detection, the answer is try YOLO. Try a version of YOLO, get your training data, apply one of these. It's off the shelf now. This idea is that you segment and then you take bounding boxes and then you fuse the bounding boxes to get the final detection. All of them, work. Now, whether it's YOLO 5 or YOLO Extra or YOLO 9000 or which version of YOLO, they're already GitHub, try one at a time and see which one works. Another challenge when we try to apply this problem of discriminative learning in remote sensing is what's called change detection. And I think this is one of the most interesting applications in remote sensing. The idea is that you have changes that might be natural, like changes in lighting, atmospheric conditions, seasonality, and so forth, but you might have unnatural changes, like built-up areas, right? Somewhere that you actually do. So this is a situation where you want to identify this. And the question is, how do I separate changes which are normal variation versus changes where it's attributed to something different, like cleaning, construction process. The second question is, how do I get high quality data? Right? Who's going to sit and going to say before and after images and hand annotate that? So we find a way around it. So that's another interesting topic. Most of the situations you have multiple instances. So if you want to find changes, it's a good idea to have a lot of observations so that you actually capture the normal variation, the seasonality. So you somehow capture that. So you find something which is unnatural, it's easy to identify. And then there's potentially heterogeneity, right? So you might have one satellite producing one type of data, then another satellite trying to fuse them together. This is a standard technique called Siamese network, Siamese twins. So this is a type of generic class convolutional neural networks where you have two streams and you have a reference stream and a test stream. So you have one image and another. And what's trying to say is trying to find the differences between those two images. So you take this, these are convolution and pooling operator, convolution and pooling, fully connected, deconvolution, which is just a reverse convolution operator. So blah, 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 you do this on every stream, and then you end up with vectors. And what you do is you apply softmax and comparison of these vectors, right? So this is one variation of a convolutional neural network that has this two-stream approach that can take two instances at the same time and produce this change map that tells you whatever options changes. And sort of wrapping this up, it's interesting thing about, especially when the change vector involves lambda. You have one situation like that where you have a previous image and the current image, and you have a neural network which is sort of stripped in the middle, like the unit that I was telling you before about Aladdin. So it's like some features from before, some features from after, and then fuse them. And then as an output, get one mark with the uncovered change. So that's one idea. Or another idea is like, you have a system that has uncovered prediction, so neural network with uncovered prediction, and then compare this uncovered prediction to the previous uncovered prediction. So it's not which one is best. Like, it is best to compare raw data and use this raw data and neural network to directly extract the changes, or is it better to extract information from any individual image and then do a comparison in a much higher representation space, which already have uncovered here, so it's just subtracting changes. So it's not clear, and there are different, especially when you think about it like operationally, like making this most of the time. There are different issues that someone needs to address. For example, what about memory requirements? Does this take more memory or this? What about complexity? What about speed? Does it affect accuracy? So there is the question of, I'm going to try to implement something and get some results. And then the question is, if I'm trying to implement this and get some results, how do I make it operational? How do I make it a system, operational system that's going to directly get any observation from web services, web services, apply my technique, produce the output, and do that 24/7. So when you try to do a remote sensing based in learning technique that is operational, you have in addition to accuracy, which is always key, think about aspects like memory, complexity, and how it affects speed and requirements and power consumption and so forth. And these are just some results. You can see, similar to what I said before, that in image classification, everybody gets 99%, so the problem is solved. So this is definitely not problem solved, right? So these are different techniques, so these are different convolutional neural network type architecture, and you see there is significant variation in what you get, right? So this is the reference, this is the ground truth. So this unit plus, which is the variation of unit. So unit is fairly old by now, so this is very new paper. So unit is very old, so there was some extension to the unit, which makes it unit plus, and you can see that extension of this basic model probably gets the best results, at least visually. So visually, this one is closest to this one. It's not perfect, it's not 99% accuracy, you still have fuzzy. So you want to write a paper, write a paper on this instead of specification. But the same architecture, same architecture will be able to get state-of-the-art performance. So this is a take-home message. Any questions, thoughts? Yes.
Do these models can provide you
The off-the-shelf models does provide you with an output, doesn't provide you a system. Now, one would argue that, okay, maybe if I don't have a system when I'm trying to classify images like that, but maybe if I have a system like the one I was showing you, the 98% accuracy, the one we have an image and you try to classify this image, right? So maybe I can get uncertainties on that. And one way of thinking about this is like, if I have a vector as an output, this element in the vector corresponds to a class, I would expect that if the correct class is the element, the second element, if I have something that is just this one, the system should be certain. If it's spread out across classes, maybe the system is not that certain. That is a valid motivation and a valid intuition, but it's wrong. It's not the proper way of quantifying uncertainty. Uncertainty quantification is a big topic, we're not going to touch upon it. There are ways of doing that. For regression, it's easier because for regression, you can always say that my output of a neural network is a Gaussian, so you can estimate always the mean value and the standard deviation. So instead of one value, you estimate two, so you always have Gaussian. For classification, it's not obvious. What does it mean to have like a Gaussian? What a Gaussian is like 50% cut and then 20% dog. It's like doesn't make a difference. Doesn't make any sense. So it's not obvious how to quantify a certain. And there are situations like out of object, out of distribution detection, where you train a system on specific type of classes and introduce another example from another class. The system completely fails to identify that this is something new. It's going to be 100% confident that it's a cut, or although it's a vertical. Right? So uncertainty, for sure, a lot of papers to come in this topic. Any other thoughts? Okay, so programming wise, right? So nowadays there are solutions off the shelf that you can use. TensorFlow is one of the most prolific one and the oldest one. It's made from Google. In 2015, it was open source the first time, the version 1. Now we're in version 2. Now, nowadays, if you ask someone, I want to build a neural network, which library should use, the answer will be 50% TensorFlow or 50% Python. Python is developed by Facebook, the Fair Lab. Each one has weaknesses and strengths. I'm gonna, focus on the TensorFlow because I'm old, and people that are old in this community have been using TensorFlow because it's older. Young kids now, they all like Pythons, but no, I don't. So TensorFlow, but I guess you capture from the TensorFlow, it's very easy to translate to Python. It's just like a matter of like, oh yes, or this is a capital C instead of a lowercase, things like that. It's very easy to promote this. And one of the major things that allowed this TensorFlow to become so hot is the whole idea of this built-in library called GRSS. It used to be that two stuff that you need to set up. Now it's built-in, so the new version of TensorFlow is already coding GRSS. And François Solet that made GRSS is now an employee of Google, so pretty sure they integrate fantastic. So this is one of the most prolific frameworks now for training neural networks. If some keywords about neural networks, first of all, if you want to install it in your machine, you will need to use anaconda that we were using yesterday. And yesterday we remember the very making sure that all the dependencies. So this is an exercise worth doing. And it's going to take some time, but as it was said yesterday, it's not for the faint of heart. So it's going to take some effort to make all the dependencies fine and work. But it does work. And what we're going to try to do today is we're going to try to use something called Google Colab. So it's a way of using Python or Jupyter notebooks, which using these libraries directly on the cloud. So you don't need to install anything, which is fantastic. We're going to see some examples of the building functions that are included there, and the two models that can be used to define a neural network: the sequential model, which is simple but sort of restricted, and the functional, which is more generic and potentially more difficult, not necessarily. So how do you start encoding a neural network in GRSS-APS-SSCS in Python, right? So import stuff, and then say, you know what, in the sequential model, I'm going to make a model. So this is the name of my model. It's going to be sequential. And then what I do is I start doing that. So I say model.add. So this is a function of the object model that says, you know, in this model now, the moment you start adding this equation, now you start forming what's called the computational graph, right? So it's a structure that is encoding this block diagrams of certain lines in something programming. Right, so you start saying that, and you say, you know what, I'm going to have an input, and the input is going to be a vector of 100 elements, and then I'm going to take this input with the vector, and then I'm going to connect it to another layer. So this is denoted by the dense. Dense for fully connected layers have this vertical vector-like structure in the network. And plus, you're going to put an activation, it's going to be the loop. So all this is that, you know what, my network is going to take an input with 100-dimensional vector, and then you're going to have 64 elements. So you can imagine it like this being a 100-dimensional vector as an input, and let's say, you know what, it's going to connect it to another one, which is going to be now 64. Right? And then this connection, this left connection. But you know what? And then I'm having this, and I make it 64, but then I want to make it 10. And why 10 and not 12? In this case, it's out, but you know, there is no reason why this architecture is better than the other. If you decide to put another dense layer, fine. But I'm going to put a dense layer here, I'm going to say, you know what? This 64 now outputs are going to be passed to compressed to another vector that's going to be consisting of 10 outputs, and plus you're going to have a softmax. So what that tells me is that, oh, I guess this one should probably be out, right? Because 10 is probably the number of outputs that you want, and you want to use a softmax. That means you want to interpret the output as class probabilities, right? So you want to have something which like sums to 1, it's between 0 and 1, and sums to 1. So it's probability. So it's like take by loss functions and stuff like that. Fine, so this is defining my network. So my network now is just 2 layers, one input, one hidden, and one output. In the mid layer, I have a loop. In the output, I have a softmax, so I have probabilities. And then I need to apply the compile to say, okay, now this is the design, now make the design. So the compiler will make the design. And it's going to say, you know what, I'm going to make the design. What is important is to define the loss. As I said, this is one of the most important things, like how do you measure performance? And the performance in this case, since it's a classification problem, you're taking a vector and you have 10 outputs, one of them will be 1 and the rest is 0. This is going to be a categorical constant of it for classification problems. Optimizer uses stochastic gradient descent. If you apply TensorFlow list of optimizers, it's a list of 50 different options, pick one. And then metrics is something that looks like loss, but it's like, you know, the poor version of loss. Like metrics is a way of quantifying the performance, but it's not the one I'm minimizing for. So when I'm trying to minimize, I'm trying to find the gradients, but if I get the gradients, I'm doing that on the loss. Metrics, you can put whatever metrics you want, right? You can put the metrics like, you know, whenever the output is between 1 and 5, you take the blue. Fine. Doesn't mean anything, but it's a metric. It is not a loss function. Because it's not a function, you can minimize and solve stuff like that. So this is I define my model. I compile the model to make this computational graph, and then I say, you know what? Fit. Train my model. My input is going to be heat train. So this is a tensor, TensorFlow. So X, Y, and whatever examples I have or whatever features I have in the input. And the output is whatever I'm trying to get as an output.
Epochs is how many runs is it going to take. So how many evaluation of stochastic gradient descent are you going to take over the entire data set? So 5 times. So you're going to take the entire data set. You're going to split it in groups of 32 examples. You're going to take the gradient out of 32, and you're going to do that for all the data sets. So if my data set has 300, 200, 3,200 images, and I have batches of 32, I'm going to do 100 times that. So for this 100 times, I have the entire data set. Do that 5 times. Here, batch size. You can increase the batch size. Eventually, you're going to run out of memory. So there's a limit. So you don't put batch size 156 or anything like that. It's going to break the CPU is going to run out of memory. So you increase it 32, 64. So these are like no rule of thumb size. And then this is the epochs. This is the time that takes time, right? So every epoch, every run through the entire data set is going to take like 1 minute. If you take 5, it's going to take 5 minutes. If you do 500, it's going to take 500 minutes. So the more epochs, the more likely you get a good performance, but the more time it takes. So it's a trade-off between performance and accuracy. And then once I have this, I'm done with it, I can apply the model evaluate. It's like, so I train the model. So in this case, you are given the input, you are predicting something, and you compare this something with the target, and you find the error. In the evaluate, you given the target, but always as a way of quantifying the performance. So it's not doing anything. It's going to take the test example, it's going to do all the analysis, it's going to produce something to say, this thing that they produce is how close is that to this one. And this is going to give you the number. It's not going to play the model, it's just going to produce the number. And or you can apply just the predict, in which case you don't have this, just say, okay, so if I have a new example, he test, and I apply it in the model, what will I do? So take model.predict, so take the input, it's going to produce the classes. And ideally, if this is going to be the correct class. Question? Thoughts? Yes. Yes. The loss, the batch size increases for? No. Doesn't matter. So when you do the training, you have to, the system needs to maintain internal memory, the forward pass and the backward pass. So that means a lot of data needs to be stored in memory. When you do the prediction on the inference, you don't store the intermediate because you only run it once. So you don't need all of memory, so you can increase that. Because in fact, it's not going to do anything. So you can increase that, remove that, doesn't matter. It's going to run through the entire test.
So how does this affect your performance?
In theory, the higher the batch size, the better the performance. That's not always correct. Even if that was correct, you don't increase the batch size as much as you want because you're going to run out of memory. So one would say increase the batch size up until the point where your system doesn't crash, and that's the sweet spot. Jan LeBoom, who is the father of deep learning, in a tweet says, friends don't let other friends use batch size more than 32. So this is what I do. Guys like the godfather. If you have friends, please don't do more. Why? The epochs can go as high as you want, right? The epochs that's in the 50 or 5. So that was the sequential, and it's sequential because you add one on top of the other. You sequentially add the layers. That's why you have the add. There is the option of functional, which is similar to that, so you import some stuff, but the difference now is that you find what's the input, what's the output, and then you sort of connect it in between. So you say, you know what, my system is going to take S input, so you need to load this input with a capital I, so that this is a function, right? It's going to say, okay, this is the input, so my input is going to be 184 vector, length vector, and then I'm going to put it to a tens, which is 64 plus 32. But you see how I go now, I say, my input, which is encoded through this element here, is going to be taken, and this input is going to go through to this layer now. And this is how I put it. So the input goes as an input here, and then I'm going to have an X as an output. So I'm going to take this X and put it as an input to the next layer and give me an X. And then I'm going to take this X and put it as an input to the output layer, which is going to give me a prediction. It's a similar idea, but instead of saying add, I do that with the variable. Right? So I say, inputs from here goes here, the X goes from here from there, X goes from here there, and then the prediction goes out. The reason why this is much more flexible is because you can have situations where you can mix and match, right? So you can have two inputs. If you have two inputs, you cannot run sequential format. You need to use a functional format. So you have input x and input x2, and then at some point you add a function to add them together. So to do that type of applications, you need to adhere to this functional framework, which is the one most people use. So you define the model like that. So whereas before you said I'm going to use a model which is sequential and these are the steps, I'm going to use a model where the inputs are the inputs and the outputs are the prediction. What happens in between the inputs and the output is defined in this. So if I take the input, then I know that the input should go there, and then it's going to use this x, and then this x here, and then prediction. So when I say model, parenthesis input output, this will automatically say, okay, so this is the computation of the design. This is the input, then it's defined what goes to the network, and this is the output. Again, compile, optimizer, you can use another optimizer, RMS prop is another option. Again, we need to define the loss function and the metric. We feed the data, and we can evaluate. Similar as before. I'm going to do an example, just to let you know that TensorFlow and also PyTorch. And there are plus and minuses in this technique. I mean, TensorFlow is better in terms of production capabilities. So it's easier to deploy it in an Android device or an Arduino device or in an embedded device. PyTorch is, it's more recent, you find more data sets and things like that. So if, like students coming in, like, okay, should I start using TensorFlow or PyTorch? So that's a good question. And the answer is, what is the code in GitHub that you're going to base your work on? Is it in Python or TensorFlow? Is it in TensorFlow or Python? If it's in PyTorch, use PyTorch and extend this code to Python. If it's TensorFlow, use TensorFlow. So, I don't see a clear distinction between those two. It's guided by what's available, what makes your life easier. Any questions? Okay, in the hands-on, as I said, we're going to see how we take these images, which are AID, the image classification, define a neural network, produce some outputs, and see what happens when I do pre-training. So, for economy of time, I will run the experiments myself, but the code is in GitHub, so you can do it yourself. So, this is the GitHub. So copy, take an image of, so this is the GitHub. So this is like actually you get sort of problem or whatever. And then this story here is you write yourself from the comfort of your own house. So the idea is you have the UC merged data set. We're going to try to do classification now for this session, and then the next one, denoising. Right. So for this one, so this is the code it's a Python notebook. So you can see I open the code and I can see this open in Colab. Have you seen that before? Who has seen that option before? You've seen that before, right? So this is an option that you can run direct that on Colab. So if you have a Colab, which is an environment that can execute code with Google resources for free, you can do it. So you can do that, and I did that. And you start up with something like that. So this is a typical environment in Colab. So it's a Jupyter notebook, start with the program with Node, and then you start with this. So I'm going to go through the process and run it and have some discussion. So the very first thing you need to do when you apply this is connect Google Colab to your Google Drive. Right? So there is this, if you Google it, it's going to come up the specific content. So you run this command and it's going to say, okay, so you're going to authenticate. Before that. So I'm starting Google Colab and I want to run. The first thing, I go to runtime and I select change runtime. So this one is going to say Python 3, fine. This one needs to be in GPU mode. So in the standard non-paid free version, maybe it's none. Make sure you go to the GPU. Yes. So this is my last one. You go. So as I said, you put to runtime, change runtime settings, you put the GPU. If it's not the GPU, if it's GPU, fine. Then what you do is you need to press this button here, it says connect, right? So I did it by itself now, as I was pressing the button, so it connected. Once you do that, and then you start running the code. So this code here, this snippet is for connecting this account, the Google Colab, to the Google Drive. So there's a way of automating this. I don't know, so I just copy pasted the time. But if you Google it, there's a way of automating this. You have to find some keys and then match the keys and blah, blah, blah. Okay, then load minimal number of libraries. So the stuff that we need, we're going to load 3 libraries. TensorFlow, which is the library for deep learning, NumPy, because of everything else, and matplotlib if you want to visualize anything, right? So nothing much. Then what you need to do is you need to download the data, right? So in our case, I download it and I put it in my Google Drive. So once you put it in a Google Drive, you can load it. The reason why we did step 1, which is connect the Colab to the Google Drive, is because if I download something and I place it in my Google Drive, then I can load it by using, from this Colab. So in this Colab, say, you know what, go to content. So if I go to content, so this is my Google Drive now, right? So this my drive here is my Google Drive, all my stuff from my Google Drive. So I go say, you know what, go in this directory, blah, 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 and load these images. So those are NumPy arrays. I load the images. And then I'm using this library, sklearn, to split the data in the training and testing set. So I left there are 50 different ways of doing that. I left it here so that you are familiar with this library, sklearn. Sklearn is a standard library for the machine learning, not the deep learning, but the machine learning. But it captures all of the machine learning algorithms, plus all the different techniques you need for visualizing, for performance validation, for blah, 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 splitting training. Everything is there. So if you need to know 2 libraries for doing deep learning, one is a deep learning library, TensorFlow or PyTorch, and sklearn, and NumPy. Right, so you apply this and it just, splits the data in training set and testing set. And then this function here also applies that. One good thing with Google Colab is because, it's as an interface, as a needer, you can have like information instantly, right? So this equation run here, the command run, and I can see the result now. It's 21, right? So the output. Now, every example in this case, and this is important, every example in this case, I have an image and I say, this is not an airplane. This is not a car. This is an airplane, a boat, and things like that. So in this scenario, every image is associated with a number that corresponds to a specific task. Deep learning does not understand that. So if I say, I make this assumption, I say 1 corresponds to boats, 2 corresponds to airplanes, 3 corresponds to cats, 4 corresponds to. Deep learning does not understand that. So you cannot give it numbers like that. You have to encode something in what's called the one-hot encoding. The one-hot encoding is if I have my class to be 3, what I need to do is I want to create a vector with length, the number of classes that exist. So if I have 5 classes, 6 classes, this element should have 6. And if I want to say this example corresponds to class 3, I'm going to go to the third cell, 1, 2, 3 cell, and I'm going to put 1. So this information here that my image is class 3 or my image is associated with this one hot encoded is the same. But this is what the neural network learns. And the reason it learns that is because it's well defined the number of classes. So if I have 6 cells in the vector, I have 6 potential classes. If I tell you that my class is 3, I don't know how many I have. And in neural networks, you need to be very specific in terms of what is the maximum number of classes and what are the classes. So you do this process, translating every number into this, and it does that through this function here called toCategorical. And you see, even from the arguments of this function, you can understand, okay, so you want to have something which is like it was numbers. And I want to show these numbers. Right, so you see, this is the training. So image 1, class 14, then class 16, then 7, then 11. I want to do that, and I want to translate them to vectors, and I want to know the maximum number. That's why you need the number of classes. You need to know, if I say class 3 out of how many? So you do that, and then your training data looks like that. Right, so it's the same thing. So the one is somewhere in the middle. So it's the same thing, but instead of having numbers, you have vectors of the same size as the number of classes, and one corresponding to where the vector is associated with the class. So this is how you define the input, this is how you define the output. Then you say, okay, so let's define the neural network, same as before, so sequential. I'm going to make a model, it's going to be sequential, so I need to load the fact, import this sequential module, and then I'm going to have convolution, max pooling, and dense. And flatten is just the process of making it as a vector. So you observe here, I have conv2D, so you can imagine I can have conv3D if I have 3D data. Now I'm just having one image. Max pooling 2D, I have 3D, not 4D, not 5D. The options are 1D, 2D, and 3D. That's all for now. And then I did what I did before. Say I'm going to make a model which is sequential. So this model now, it's like, okay, set up, initialize this model in sequential and start adding. So first, you're going to add a convolution, which is a 2D convolution of 32 convolutional kernels, each one of size 3 times 3. You're going to take the output and you're going to put a ReLU activation at the end. And the input is the input of my data, right? So because the first layer. And then I'm going to buy a max pooling. What does it mean? This max pooling means that for every 2 by 2 region, you're going to take the maximum value and replace it with 1. So if I take every 2 by 2 region and I replace it by a single value, that means that effectively my image, every time I apply that, gets half in 2, half and half and half. And once I do it a couple of times, now 2 times in this case, I say, you know what, now that I have made a very small image, which is not exactly image, it's something else feature, make it into a vector. So this is going to flatten, it's going to make it into a vector, and then what's a vector? It says connected through fully connected layers. Those are the dense. So the first one is 64, and then the last one is equal to the number of classes. So always the last layer is equal to the number of classes, always. And the activation is softmax always if I want to do the classification and compile. Right, so I do that. So the system will compile this. There is the function summary. So if I run this, it's going to do a printout of my network. So this is a printout. So the network, you have an input that is 254 times 252, 54 times 32. And then you do a max pooling, and then you have another convolution, and then a max pooling, and then a flatten. So you can see here the dimensionality of everything, right? So this was an input that was 32, and then it became smaller, and then it became a vector that was only a single number, and then 64. In all cases, the first element is none. This none is because it corresponds to the batch size, to how many elements you have. So it's always none, right? So you get like don't watch at this none. Just look at the rest of the numbers. And some of the stuff. So at the end says like the total number of parameters is 50 million, right? So that's 50 megabytes of data. Yes.
Top layer versus last layer.
The what? So what's the question again? Yes. So the architecture we have here is a convolution, a max pooling, convolution and max pooling, and then a flatten, right? So we have 2 convolutional layers, and then a flatten, and then 2 dense layers, 2 fully connected layers. Right? So the first convolution is the input, the second convolution is just an intermediate convolution somewhere in the middle. Okay, so this is my model, the number of parameters. Now, what I do, I train my model. So heat train is 256 times 3. So my images are 256 times 253, and I have 10,000 of this. Give me a second. The white train is the label. So in this case, it's 10,000, 1,000 examples and 21 numbers like this. And then I have the epoch and the validation data. Yes.
I don't know if this is like trying to follow along, but still just having trouble loading the
So that's the reason why we do it like that and not like step by step, because you can download the data from the link, put the data in the full drive, your drive, and then load the data from your drive. Because the data is 100 megabytes, and it takes time. Right? So don't spend time, blah, blah, blah. You can do it. Yes, sir.
That's a fast way to do it. Just have it format and then it's links it. I can help you.
It's not meant to go step by step because it's going to take a lot of time. But if you take about some question, we will talk about it. Yes.
The dimension of the image is there, right? So from where is the model knowing the dimension of the image? You printed the model, right?
Yes.
So there the dimension of the image was there.
Yes.
54, 32. 32 you have mentioned, but how is the model knowing?
So this is the output. So the output. So one of the options when you define the convolution is to talk about the padding. So what happens if you don't take anything, the system will select the values. If I have a 56 and I convert to 3 times 3, it will lose a couple of pixels at the end. That's why the 56 comes into 54. There is an option that the system can reflect and can extend the boundary so you don't mess up with the numbers. So you get 256 times 256, which is by throwing in this, the padding. The parameter padding, saying that's going to produce something that's going to take care of the edges. So it's not going to affect the output. So now the output is not the output. Solution is still going to be 56 and 56. It feeds the values by reflection, by verification. It's not that important in the sense that it's like the two columns at the end of the image. It's important for me to classify it. No. So even if I grow in the way I become 54, it's going to be the same amount of information. It's used a lot. Yes.
So if we don't one or ten would have a wide benefits, and then we use fast categorical cross entropy as an optimizer, then we will
it's not optimized, it's loss function.
Yeah, so like if we use those, so will there be any difference?
So again, categorical cross entropy is not optimized, it's loss function. So in this case, we don't have an alternative. So it's categorical cross entropy, that's it. We don't have any other option.
The sparse categorical cross entropy.
The sparse categorical cross entropy.
Yeah, if we use that without one much encoding our data.
The formal, the thing that we're going to do is apply one of the deposit things like that, and then do categorical cross. Sparse, yes, but this is optimization, right? So this is the format that's handled. So there's no extra value. In terms of performance, yes.
The first count, is it mandatory to mention the input shape?
Yes, always the first thing you need to define the input of the first layer. Only the first. The rest is fine, but the first one, yes. Yes. So once you do the convolutions, right? So if you remember, so if you see this figure here, you start from an image, you apply convolution and max pooling, convolution and max pooling, and then at this point, when you have a very large number of very small patches of 2D patches, you can take them and have, instead of having a 3D structure, which is like very small images and a lot of them, take everything and make it into a huge vector. This is what the flatten does. It takes all this 3D structure and makes it into a huge vector. It just unrolls the tension. Nothing that's important. But you need to do that if you want to apply events. Like this layer here, the full connect, those are events. And so this is pretty much encoding what we're doing now. We have a convolutional layer with patch pooling plus 2 full connect at the end. So this is pretty much what we're doing now. Okay, summary, do the summary, then train the model. Right, so you apply the train the model, and it's going to take some time to train the model. It's a small version now, so it's not going to take a lot. As I said, what you need to do is, what is the training set? What is the output, right? So this is the images, and these are the labels. The batch size, 64, 32, 16, depending on the scenario. Epochs, the more the merrier. And validation data, if you want to give some part of it for validation. You start, and what you get in printout is in every epoch, so in every run of all the data, you have the value of the loss function. In our case, we also can have accuracy. So loss function, does it go up or does it go down? What should it do? Go down. What about accuracy? Up. Right? So loss function, which is what you pay, which is the categorical cross entropy, should go down. Accuracy, which is something that I'm looking for accuracy, but it's not the one that I'm optimizing for, should go up. And you see that indeed, the categorical the categorical cross entropy goes out and the accuracy goes up. However, you also see that in the validation data set, whereas in the training set I'm getting 96% accuracy, in the validation set that's 20% accuracy. So that's really, really bad performance, right? So the system is like it's failing. And you can see that here, right? So this plot here that takes, what is the impact of the accuracy, let's say, with respect to the epoch. And you can see the more time we spend with gradient descent of the data, the system becomes better and better. But it's actually overfitting because it's becoming better and better on the training set, but on the test set, it's doing almost nothing, right? So it's becoming almost constant or very small increase. And you can also see that in the loss, now it's not the plot out is due to scaling, it looks like that, but you see similar situation, right? So whereas the training loss goes down, the validation set doesn't. Why? Because you allow the system for 10 epochs, right? So it's a small amount of time. And the network might not be optimized because it's a very simple network. So what can I do? Well, what you can do is you can exploit this and apply that. Yes, I'm going to find that the layer is very bad. What you can say, I come up with this network. That's really bad. I wonder if all the good people in the computer vision that spend hours coming up with like very specific deep learning models for classification can help me out in this situation. And the answer is yes. We can use a pre-trained model, so we can use one of the techniques called, one of the models called ResNet. You remember the ResNet architecture? That was the one that can go really deep. And you can use a network which is 50 layers. So our case was only 2 layers. But this is the of the self architecture with 50 layers. And you say, well, go and download this pre-trained architecture on ResNet with the weights found by training on the ImageNet. So this is effort and money spent by Google in training this ImageNet for 1,000 epochs or 1 million images for natural images, and do that, and then make sure you get me everything, but don't include the top layer, because the top layer has to do with classification. It was meant to classify images of cats and dogs. I don't want to classify images of cats and dogs, but give it the whole thing, except the very last thing that doesn't actually assign classes. So once you do that, you say, you know what, get me a ResNet that is already pre-trained, and the system will automatically download. Says, now, in this, I'm going to fine-tune this. So I'm going to make sure that my system is optimized for my data. Right? So the aerial classification data that I'm using here. How do I do that? I go to every layer of this unit and I say, you know what? You are not trainable. So you're not going to change the values in all the 50 layers, except the output layer. So how do you create this output layer? It says, you're going to take the input, and this output that you get from the base layer, you're going to put it in what's called a global average pooling layer. So this is another pooling layer that just groups together information. Dense, similar to before, and another dense to get the output. So what I do is I take 50 layers from this pre-trained network, and then I just add 2 of my own layers, fully connected layers for my own specific problems. For example, the output of my second-best layers is equal to the number of classes. I have 21 classes. ImageNet has 1,000 classes. So that won't work. So throw away this and keep this. And then I say, you know what? Now my model is something that is as input what the base model takes as input. So use the input of the base model, run it through the base model, and then the output is going to naturally come up from this one. And you see this architecture here is the functional. So you don't have add. To demonstrate what's happening, it's gonna appear here that the input is the base model. So the base model, now this base model is going to produce X, and this X is going to be the input here. It's going to produce a new X, and this X is going to be here. So by the variables I define the functional for, and you say, run the data. So the system will go, will automatically go and download the data, the pre-trained model. And then I say, okay, so now take this model, take all but the last 2 layers out of the 50 and fine-tune, apply the greedy descent on this, and keep the rest of them as it is by training in ImageNet, in cats and dogs. And what can you do? Right, so this is going to run for 5 epochs now. In terms of accuracy, I'm starting very well from 64%. But in terms of validation accuracy, 88%. That's something. Remember, before it was like 13, right? Or 20. Now I'm starting in the validation set, which is the thing that I'm actually interested in, and it's becoming 88, now 93, now 91. So with the same amount of data, with an off-the-shelf network that I do with pre-trained in a completely different scenario, and with a very small number of iterations, I'm using now 5 epochs together, I'm getting performance that in the validation set, it's 99%, like 90% on AIT data set. And when I apply, indeed, the output is, you hear the question?
I mean, you can't
So your question might be phrased as, okay, so that's great, but my data are Landsat 8 and they have 14 bands. This one works for 3 bands. What can I do? Well, sorry. It's not as trivial. It's not like you can take off the shelf and use it. You can say, okay, I'm going to take these 13 bands or 14 bands and I'm going to apply 1 layer that's going to make them 3 and then use the rest of the pre-trained. That's fine. I'm going to take the first 3 and I'm going to have 3 different ResNets, each one on each 3 bands, because that's the way it is defined. So what I'd like to say is that you're always constrained by what the predefined network is supposed to do. So if the predefined network is made of analyzing images of 256 times 256 times 3, that's the type of data you need to have. If you have bigger images, crop them. If you have more bands, come up with a way of solving them, right? If you have some which are like 2 numbers, it doesn't work. So this is just a tutorial to demonstrate. But if you have aerial images like this data set, which is like RGB, then fine. And you can see here, it's fantastic, right? And you can see the performance in the same thing. So just 5 epochs and you go, almost 1% and then 95, 94%, right? And the same thing goes for the loss. Right, so just doing this simple change that we had now, using the whole idea of pre-training a network, you can have performance look like that. So this is the confusion matrix, like prediction versus actual classes. And it's like, you have a couple of errors here, but it's mostly on the diagonal. What is this? So this is a confusion matrix. A confusion matrix is a way of visualizing results where rows corresponds to predictions and rows correspond to prediction, columns correspond to prediction, and rows corresponds to the graph or vice versa. It doesn't matter. So the whole idea is that this number here tells me that in my system, for out of the 46 examples that were from class 10, which is like Harbor, all of them were classified to class 10. You might have situations like that. So out of the 40 something examples from class 6, 34 of them went to the correct class, 9 of them went to somewhere else. So when you make a confusion matrix like that, you would like to see something that's completely diagonal. So the prediction and the ground truth is exactly one-to-one. You won't see, you're going to see square. And the question is how much is the spread? So here you have minimal spread. So here, but they are small, which means that the system is doing well. But the spread across diagonal is an indicator of how well my system is doing, and there are metrics to that. And these are just some. So visualization, right? So it was predicted 3, and it's actually it's 100%. This one failed, right? So it predicted class number 2. It was actually class number 11. I don't remember the names. And this one. But in general, using this mechanic was a huge increase that you saw that. And you take the neural network and say, you know what, I don't want to use that, I want to use something else. Then there's a lot of building functions that we can use and networks that we can use. And but this is the baseline. Yes. You need to download them in Google Drive, put them in a folder, and then in the code that says, this is the link to my drive. So you need to change that, the path. Reshaping.
So the issue with the data is still loading. So the solution was to add it into your drive as a shortcut instead of directly downloading it. So that you're just linking to the drive where the data is already loaded. So the reshape here is occurring because it's not fully synced yet, because it's still calculating on the collab. So it looks like it's some other kind of error, but it's actually just.
So you solve it by using the shortcut.
Yeah.
Any other? Yes.
Can you technically put in any size maps?
No, you need to define the size, right? So you need to know the size, but if you're not constrained by using an off-the-shelf network retrain, but you define your own, you can do whatever the size you want. What's the added value of getting like really big images? So it's gonna take a lot of time, but it's not gonna help you something. But yeah, yes.
If you're building your own architecture, what is the best way to tune the maybe option of like efforts or
So it's rule of thumb and it's experience and expertise. And there are some techniques. There are some libraries where you can actually, there's one called autoencoders, where you can say, what, make me a network that I'm not exactly sure how this is made with 2 layers, maybe 3, maybe 4. So you give it some parameters on the range of stuff, and the system will set all these different architectures to find which one is the best. This is called network architecture set, but you can imagine that this will take a lot of time because you're going to look for different architectures to find which one is the best. So, in my experience, the best thing is to start with a pre-trained model so that you know that someone has some effort, so you do incremental updates to that instead of starting. Okay, guys, moving on to the next session. So the things that we talked about so far here through the whole idea of classification. You're taking an image and you try to classify every pixel, every region, every object, whatever. Now the other big domain of deep learning is what's called generative models, and including inverse models. So this is the situation. So in inverse problems, what you're given is, you're not given an image and you're trying to classify this image or associate it with some labels. You're given maybe a low quality image and you'd like to have a high quality. Right? So the domain of input and output is the same, but it's different characteristics. So for example, this is a situation of an example of an image that I get from Sentinel, and this is the same picture when I get it from Google, which is a private transparent satellite. And you can see the difference in resolution is amazing. Right? It's huge. So one would say, okay, is there a way of formulating this problem so that I take this type of observation from Sentinel, and then I apply my techniques to get out with screw like that? And this is the inverse problem. It's called the inverse problem because the idea that you somehow have this idea of getting high resolution, nice data, and the forward model is something that affects that and makes it worse. It's the government of the system, the atmospheric distortions, it's the motions. All these effects will make it something that's going to take the nice clean image and going to make it really bad. And this is what you get, the really bad image. So what you do is you try to invert this process. Okay, I invert all this degradation that happens to the image and go from this low quality to this one which is higher quality, without noise and so forth. So this is one class of the inverse of the generative model, the inverse models, and that is the generative model where we're going to touch on them. And the whole idea is that if I get examples that produce a distribution, I would like to learn this distribution of this example, so I can draw from this distribution, right? So I can completely characterize my data, and then I can generate new data, which is very useful for a lot of applications. So we're going to start with the inverse problem. So a very standard problem in the inverse problem is what's called super resolution. So in super resolution, you give a low space resolution image times, and we're going to find the neural network that's going to make it n times n, where n is bigger than n, right? So but that's called super resolution. Effectively, you can do that because in reality you don't have situations where you have like low quality and high quality. The satellite is there, or the drone is there, and it's taking this type of image. That's it, there's no options. And so what you do is you do this process called bulk protocol, which is you take nice clean images, you apply the process of making bulk, which is like down something and blurring and adding noise to yourself. And then what you do is you take this and assume that this is the ground truth, this is the thing that I'm trying to find, and all this operator will produce this. And then my neural network will take this as an input and do the inverse. And get from this low quality downgrade the blurry image to this high quality. That's why it's called the inverse problem. Yes.
So can't we use singular value decomposition for reducing the resolution rather than using machine learning?
First of all, I don't want to reduce the resolution, I want to increase. You're talking about this process. So this is the process I do it mechanically. So effectively what you do is you guide it to some linear operation. As we did not necessarily, it's like it's a low pass filtering. So then it's a low pass filtering, then you have those and ways, and this does something does the operator that does some samples, right? So effectively this is a very standard technique, right? So I didn't, right? But the equation is that if you have some clean input X, what you get as an output is H times B times X. So you have this image which is blurred and then down some, right? Now these are linear operators that this process.
Interesting.
It's matrices, yes. And potentially they are low rank, but not necessarily. So you want to do the opposite. So one question that is important is that whereas in the previous case when we get the images and try to classify with measures of accuracy, you find the correct class, yes or no, perfect. In this case, there is no notion of accuracy. What accuracy? What do you mean? I mean, I'm having an image and I'm comparing to another image. So you need metrics to compare images. So this metrics to compare images, the standard metric is the mean square error, which is the difference. PSNR equals to the signal noise ratio, which is like another way of comparing the errors. And another image-based metric called SIF, structural similarity index, that looks like that, takes the mean values and the standard deviations and does some complicated process. Then comes up with a number which is from 0 to 1. Mean square error is the standard loss function and metric we're going to be using in this technique. These are an extra stuff, interesting stuff, but mean square error is the metric, which is the loss as well. So this is what we're trying to minimize. We're going to try to find the gradients, minimize the effect of this gradient, so that in terms of mean square error, I have the smallest number of the smallest value. And then given that, so this is how I measure the performance. Now the question is, okay, in this example, you're given one image and you're trying to increase. Are there analysis scenarios? Yes, you can have a situation where you have multiple frames and you try to increase all of them. So you can think about this like a video, like small video, or sequence of images. And then you can have a situation where I don't want to increase necessarily the spectral resolution, the spatial resolution. I would like to increase, for example, the spectral resolution. So going from 3 bands to 12 bands, can I do that? So this is called multispectral resolution and multi-differential resolution spectrum. So the standard technique for doing natural image and more sensitive resolution came up in 2015, which is the super resolution CNN. So this was the simplest neural network we think of. It's just 2 layers, one convolution, another convolution. In this case, observe there is no max pooling. Why? We don't want to reduce the size of the image at the same, so we don't want to reduce. So no max pooling. So it's much easier because we have only convolution and the loop and only linearity, and it's 2 layers. And this is like 50,000 citations. So this paper here that came up with this idea. So that was the state of the art back then, right? So that like KSVT, local linear embedding, so non-deep learning technique. That was the first deep learning technique, very easy. You can see, some of the benefits that it was able to, give it more time and more epochs to run the gradient descent. It was able to surpass state of the art, and it did it also in terms of visual quality, but also PSNR. PSNR we measured in dB. Even an increase in PSNR is very, very big, even decimals. Even an increase of almost 2 dB, it's almost unheard of. So that's like huge difference. Right? 2 dB is not like 2% accuracy. So 2% accuracy is really big. 2 dB increase is like fantastic. Huge. So you got huge performance results that was played. And then the idea is like, okay, so maybe 2 layers per day, what about having like 50 layers? Maybe that's better because the same thing was happening on the classification scenario as well. So they tried to do that. So they make an idea that made this idea. So the idea is that in the image, you put convolution and ReLU, again, no max pooling, similar layers. You do that, but here's the interesting part. Instead of having an image and try to directly estimate the higher quality of the image, try to take the image and then estimate the residual between an interpolated version of this image and what you get of this. So the network, it was not trying to learn to generate the image itself. The network was trying to see, so if I have an image and I do some interpolation and I increase it, what's the extra stuff I need to do that so that it becomes perfect? Right, so that's very good. So here you only have to learn the extra stuff to go from the standard like interpolation to the extra performance, compared to other techniques that need to learn the whole process. So this residual connection here that allowed this to become very deep super resolution was, a game changer, fantastic performance. And this is still one of the best performance techniques so far. And then you can have the option of multi-scale. So doing this analysis across different scales, right? So times 2, 4 times 4, 8 times 4, and so on. I think we're supposed to have a break now, right? No? So anyway, let's continue for like 5 more minutes until it's 2:30. Yes, and yes.
Right, input is the low resolution image and output is high resolution. So the low resolution dimension would be lower than the high resolution, right?
Yes.
How is the dimension?
Okay. So what this techniques do is they we're going to start from low resolution to high resolution, but we don't want to have this issue with the dimension. So we take the low resolution, we do any off-the-shelf interpolation to make it to a proper PV resolution. In terms of pixels, though, only the quality is going to be really bad. But in terms of size, it's going to be the correct size. So everything is the same size. So you apply this process on the same size. Right? So this is an interpolated low resolution. Right? So you start from the interpolation, which is like very easy to do and very cost efficient and so forth. So you start there and you enhance the information. So you don't get this situation with the sizes. And then, one of the last things that came out in this super resolution technique was the enhanced deep super resolution. That did so different stuff. So, one of the things that they sort of modified the architecture of the neural network, and then they put these blocks and then the residual. So, using the standard techniques, the standard known hacks like convolution, and then the whole idea of residuals and putting more residuals. So putting them together was able to show much better performance. One of the interesting things of this technique was that this is exactly the point that the colleagues was making here, that you start from a small image and then you sort of increase the size of the image so that it's consistent along the network. In this case, it does that. It doesn't have to increase the image itself. So what it does is, if I want to increase my image times 4, I'm going to take one image and I'm sort of trying to create 4 other images. When I reshuffle them, when I rearrange them, this 4 times whatever resolution is that, and times n is going to be 1, 4 times n, 4 times n. So you increase the resolution, but in constructing the depth into size. And so you don't need to follow the details. It's an interesting technique, and if you use this technique, it's much more efficient and it's got better performance. And variations like, okay, so maybe we can like extract the features from the SRCNN, which is the standard technique, and then do this that incrementally increases the resolution. So you start from a small image and then increase it times 2, and then increases another times 2, and then increase another times 2 in order to get eventually to times 8. So you progressively increase that. Now, this similar to what I showed you in the previous session, this is a paper last year, which does a review of deep learning based on remote sensing super resolution. So we're talking about today. And these are different CNN-based methods, and these are different satellites that they use for training. So this is called View3, and this is Pleiades. Both of them, the qualities are pristine. It's like centimeter level resolution. It's not like Sentinel. And what they try to do is try to do the super resolution. And this is the performance you get. So look at the PSNR, 32.5, 30.8, 0.6, 0.6, 0.9. So this paper that came in last year, compared to this one that came in, the VDSR that came up 4 years, 5 years back, the difference is 0.1 dB. So that's noise. I mean, it's variation, you cannot see that. If you are in experiments again, maybe give different results. So the take-home message that this problem is completely unsolved. Whereas in the previous case, you get 99%, it's like it's problem solved. This, no matter what we do, no matter how we modify this, in most of the cases, we don't see like a significant increase in terms of performance. So whereas the classification is a problem that is very well thought out and people have progressed a lot in terms of analysis, in terms of enhancement, like super resolution, the situation is much more striking, right? So you can see that for this data set, evolution in the last 10 years is almost nothing, right? That's people. In here, yeah, okay, so I'm getting something. But in terms of like this structural similarity index that goes from 0 to 1, let's say I need to go to the 4th digit to see any difference. Right? So so the question is, I know how to implement this technique. Now I need to read the paper to do this and then this and then this and then this. Will I get any pilots how to my extra this papers? Not so much. I mean, this is what I do. So whereas the classification is a problem solved, this is problem almost completely unsolved because none of them is definitely better than any of the others. Any questions on those thoughts? Yes. This is not classification. This is.
So, this model is prepared, and how can we implement this model to be actually performing? It's not a language compared and it's always just I want to implement this model for other images and the other area where I'm. Is there any other procedures to implementing this?
So the question, you train this in one area, you want to apply in a different area. Machine learning theory tells us that if the range is set to get in one area, matches or closely similar to the other area, you shouldn't need to do anything. The system should work for the other area. That's the idea. And the underlying theory of all machine learning is that the distribution of the training set and the validation set is the same. So if I'm training a system that is, looking at that cover where most of the pixels in the image are forests, and then I take the system that is been trained fantastically on the Amazon rainforest, and then apply it to LA, it's not going to work. It's not the system problem, it's not the data problem, it's my design problem. Because my distribution of examples that I use for training is completely different than the distribution of data I use for testing. Because I train in Amazon and then I test in LA. So you need to make sure that my data, the training data matches the testing data, at least in terms of characteristics. Yes.
In expert resolution, we want to maximize the value of SSIM.
Yes.
All the values we want to maximize.
All the other one?
The values we want to maximize them.
No, this one has to be small, and this one has to be small. Yeah, you know what? I forget about this. Listen, these are the important. The other one.
Okay, so maximum value that SSIM can find is 1. So it is getting nearby 1. So why is this still not a solved problem and it's a problem? Unsolved problem.
My argument that it's unsolved because all of them are doing the same, but if your argument's like they're all doing the same because it's fantastic, then maybe it's a problem solved. Yeah, okay. I mean, sure. Problem solved, unsolved. Research-wise, don't put your money there, right? Because it's a difficult problem. Like whether if I get a situation where I get my data and my data is low resolution, when I increase the resolution, whatever I'm going to do, I'm going to apply one of these. Now, the true question that is not shown here is like to define whether this problem is solved or not. It's not about the deep learning techniques too, because each deep learning technique takes time to train, time to inference. Like if I do my Euclid interpolation, right? So the most standard thing that is included everywhere. If I do that, what's the SSIM that I'm getting? Because if I do that, and the SSIM that I'm getting is 0.98, that means that my problem was easy. My problem was easy. Because if you do something which has been on for like 50 years now, and zero training and zero, it's a simple thing you do, and you still get fantastic performance, that was an easy problem. So 99, 0.99, a very easy problem doesn't get much. But the arguments, you can follow them to the opposite of the head. That's not my work. So they decided to do that. But if you are like, truly see whether there is merit in doing all this stuff, do the baseline. The baseline is not much. By Euclid interpolation, how much do I get there? The question's another day. Yes.
What are the limitations on how far in resolution you can get?
It's usually times 2, times 4, times 8. You have to be very pushy and very fine, and that's it. Times 2, times 4.
Is there a way to do that to times?
Sure. Well, I don't know how to do that. If I did, I would write the paper. But yes, of course, you can increase. I mean, as a goal, it's like fantastic. Yes. This scenario is for single image super resolution. So you take one image of specific resolution to get it to another, the same image as a different resolution. So it's 1 to 1. So it's not that flexible, combining all that stuff. You can do it. And this is closely related to what's called path sharpening. In path sharpening, you have low resolution high resolution paradigmatic and you use them. Yes, indeed, and there are papers to do that. It's a bit more involved than that, but similar idea. But yes, but it's not super resolution. It's more closely to fusion or path sharpening. Not super resolution. you do the same thing in partial, right? So in partial, you again try to get super resolution.